Where'd he go? I guess he's coming back.
Okay, so this equation. On this lens. This time, that is okay, so last time we did a homogeneous equation, right? With with a zero boundary condition. But we did the rigid type boundary condition. So we derived a series solution using separation of variables method. So today I want to ask you quickly, just a quick review. So did you try this one, a different boundary condition? If you have tried, if you haven't, I want to ask you to give me at least
different boundary boundary conditions or
yeah. Last time we did for the rigid boundary condition, right? We derived the solution in series form. Yeah. So this is a Neumann zero boundary condition, just slightly different boundary condition. Yeah, the problem with the different boundary condition, right? This problem is overall still wave equation with the different boundary condition. So still we have initial condition, another initial.
but now just the boundary condition, the partial with respect to x
Yeah.
of 0 to
Yeah. So I want you to apply the same process. Just quickly to tell me. So because we use separation of variables, that is we assume our solution u as a function of two variables, right, can be written as a product form. So that is the product of a function of x and a function of t. Yeah. So we know this function will satisfy what condition after you substitute that product form into the equation itself. So we have just substitute this one. So that's a second order derivative with t minus second order derivative with x. Right, when you substitute that form into the equation, then we have an eigenvalue problem. Remember the function phi, if you move to the other side, that's phi double prime over phi, and this is the h double prime over c squared, actually as a function of t. So this has to be equal to a constant, because that is a quantity depending on t only, right? This is depending on x only, so that has to be a constant. Constant, then we use that notation because we will prove lambda has to be non-negative. Yeah. So we use the notation. So, but now let's see. There's one ODE we found. So this is just the ODE. Second order. This is the eigenvalue problem. ODE problem. And then there's a boundary condition, because now you are looking at a different type. So this phi will satisfy a certain boundary condition. You see this, for this form, to satisfy that boundary condition, phi has to, the derivative of phi at 0 will have to be equal to the derivative of phi at L, right? Equal 0. So that's the difference. Okay, so because the solution should satisfy equation and boundary condition. Yeah, because of the boundary condition, we arrive at the conclusion that the phi should satisfy this boundary condition. Okay, then the h is the quickly, so h actually will satisfy another second order ODE, right? So we have this. Of the derivative of t equals negative lambda c square h t. So this is the so then this one, if you solve it, consider three different cases still like before. So we consider when lambda is negative, when lambda is 0, when lambda is positive. Then we solve. Let's try to get phi first, and then we get h. Then we will get a solution in that form. Yeah. So let's quickly get solution. What is when lambda is negative? Just as before, we just write down our general solution, right? We know how to solve the second order equations. General solution will be this form. Phi hyperbolic cosine negative lambda x and then hyperbolic sine square root of negative lambda x, correct? Yeah. And when lambda is 0, that second derivative is 0, so that means the function has to be a linear function. So then this is a function of this form. Yeah. And then when lambda is positive, then this is we have a general solution phi cosine. Because you will have for the characteristic polynomial you will have complex roots. So you have alpha cosine and lambda is positive. Alpha cosine this plus beta square root of lambda. Three different cases.
Sine square root of
Beta.
lambda. Oh, beta sine square root of lambda?
Oh yes, sorry. Yeah. Sine square root of lambda x. Correct. Okay, so we have general solutions. And then we discuss for all in order for a problem to satisfy, but right now those are general solutions, right? Satisfying the equation. We have to determine alpha beta so that they will satisfy the boundary conditions. So now alpha beta to be determined. Okay, let's try. If you use that form, you substitute into this the boundary condition. If you take a derivative, you will get alpha hyperbolic sine. Beta hyperbolic cosine something, right? Times some constant. So
it will not be 0.
Yeah, this sine, hyperbolic sine is 0, it will be 0. So then you conclude the beta has to be 0. Yeah, beta has to be 0. Then try the other one, you get a 0 also. So that means for the solution of this form, to satisfy boundary condition, you have only trivial solution. Yeah, so that's not our interest, right? We're not looking for trivial solutions because of the initial data. Okay, so that's not an option. Next, for the linear function, if you take a derivative, you get beta. For the beta to be, it's a constant, right? The derivative is constant, but that means the derivative function has to be 0. Then beta is 0. Yeah, so that means beta is 0, but alpha can be arbitrary, right? So we can find a non-trivial solution in that form, right? Alpha is just a constant. So it's possible, yeah, for this. So let's just consider the boundary condition. We can determine alpha and beta in that form, in the linear function. Okay, so this is because beta has to be 0. So alpha is non-zero, constant. So this solution is unique up to a constant multiple of this one. Because you can put any constant, right? You can put alpha, still a solution, right? You see the solution, if it's a constant, you take a derivative, still get 0, right, at both sides. So it's unique up to arbitrary constant. So we just put a 1 here. Any arbitrary multiple of 1 is still a solution. Okay, so let's look at another one. Next one, you take a derivative. Make it, so take a derivative first. So that's
Negative
alpha. Yeah, so hyperbolic sign, right? Negative.
negative.
And also when you square root of lambda
Yeah.
over here. So a chain rule. And this is derivative of sine cosine, then derivative of inner function square root of lambda. A chain rule. So we put it here. Okay, now this is derivative, but take a 0. We substitute a 0 into the derivative function. So when it's 0, that's gone. Right, sine function, that's gone. This,
It's left with beta squared of lambda.
yeah, so this should be 0 as a 0 boundary condition. Should be 0. So what's your conclusion?
Beta squared.
But I put 0 here because that's a 1, right? That's a 1. Yeah, so beta has to be 0. Yeah. Because lambda is positive in the third case. So beta has to be 0. So now that means your phi has only one term, right? Beta is 0. So now let's look at this term only. Just one term. So for this one, this function with one term only, we satisfy the second boundary condition. So the derivative, which is only this, right? Just this term. This term, when x equals L, this has to be 0. So let's make it, so the derivative of this one term. When x is L, this has to be 0. So notice, can alpha be 0? Because the product is 0, one of them has to be 0, right? One of the factors. Can alpha be 0? Because beta is already 0. If alpha is also 0,
Trivial.
the phi is identically 0. It's a trivial solution, so no. So we don't want to make alpha 0. Instead, we can let this one, because lambda is non-negative, right? Lambda is positive here. So that's not 0. That's not 0. Then this one, in order to find a non-trivial solution, this one has to be, sine function has to be 0. Yeah. So make it sine value 0, so that we find those will be multiple of pi. Yeah.